Hello everyone and welcome to the iSystem webinar series. Today's session is about debug and trace on NXP S32K3xx. You will learn about the different debug and trace features of the low power ARM Cortex-M based controllers and experience a live demo in winIDEA showing different use cases. My name is Sabrina Kisslinger. I'll be the moderator today. Today's speaker is Manish Kumar, who will lead you through the technical presentation. Hi, Manish. Manish is application engineer at iSystem. His previous work experience in the automotive industry as an embedded software developer and system engineer makes him best understand the issues of software development and user applications. So that's it from my side. Over to you, Manish.
Hello everyone and welcome from my side. So let's begin. So this webinar will help you to understand the debug and trace architecture of S32K3xx microcontrollers. I will talk about S32K3xx specific debug and trace features. I will also explain the required winIDEA configuration to make use of these debug and trace features. At the end, I will do a live demo session where different use cases such as program flow trace, data trace, function profiling will be discussed. So our today's agendas are, at first, to give you a short introduction to S32K3xx microcontrollers, followed by that discussing its specific debug and trace features, and later part of this webinar to have a live demo session where required winIDEA configurations, tool setups, and few use cases will be discussed. Now let's talk briefly about S32K3xx architecture. It has 32-bit ARM Cortex-M7 core which can execute up to 160 MHz. Each core has up to 8 MB of program flash memory, up to 256 KB of data flash memory, up to 1 MB of SRAM, up to 96 KB tightly coupled memory with each core, and a quad SPI. Apart from that, actually S32K3xx microcontroller family are either single core or multi-core. For multi-core microcontroller, operating mode can be either decoupled or lockstep. If they are in lockstep, then the checkers core execute the same code after a delay of 2 cycles. Apart from these information, few other things to know about. Each core has an MPU, which is memory protection unit for dynamic task protections. Finally, but rather more important to know, debug and flash programming can be done via JTAG or SWD. Based on the previous slide information, S32K3xx microcontroller family basically implies either single core or multi-core. If it is a single core microcontroller, then life is a bit simpler. But if it is a multi-core, then definitely not so easy. So in case of multi-core, from the debug tool perspective, I'm going to discuss few challenges. And the challenges are, first one is operating modes, second one is control and display, and the third one is core synchronization. So let's talk about operating modes. Actually, this chip supports 2 operating modes. First one is decoupled or independent, and the second one is coupled or lockstep. If the operating mode is decoupled or independent, all cores works independently, while in lockstep, one core starts executing after a delay of 2 cycles. From debugger perspective, a lockstep core behaves like one, and we can see only one core. Now let's talk about control and display. In decoupled or independent operating mode, a separate winIDEA instances are present for each core. winIDEA instance for each core makes the working environment more friendly and easy. We also support SMP where both cores can be debugged in one winIDEA instance. Now moving to core synchronization. In response to core synchronization, a bidirectional core control is possible. The CTI, which is cross-trigger interface, and CTM, cross-trigger matrix, these two modules are being used to achieve this. About core synchronization, I will explain in bit more detail in the later segment of this webinar. And during the live demo session, I will show you the required winIDEA configuration as well. So at the moment, just stay tuned. Now let's talk about debug and trace architecture of S32K3xx microcontrollers. The modules which we see here in this diagram: ETM, embedded trace macrocell; DWT, data watch point and trace; ITM, instrumentation trace macrocell; CTI, cross trigger interface; CTM, cross trigger matrix; ETF, embedded trace FIFO; TPIU, trace port interface unit. I mean, these modules are called ARM Coresight IPs. So the manufacturer of a microcontroller basically integrates Cortex M7 core along with the required Coresight IP modules to create a complete CPU subsystem. Now here, one more important thing to know about is how the chip can be accessed by the debugger. And the answer is either through JTAG or SWD interface. Behind that, there are so-called access port to access on-chip resources like memory or peripherals via the system bus. In addition to that, all debug and trace related modules can be accessed too. Now let's talk about run control and breakpoint unit. Basically, this unit controls the instruction execution of the core. That is, they provide functions like run, halt, instruction stepping, as well as instruction breakpoints. The trace related Coresight modules like ETM, DWT, ITM, basically these modules are closely attached to each Cortex M7 core. The data generated by these three modules are routed into ETF and then followed by the TPIU to trace output ports. This microcontroller family supports two types of trace ports. First one is parallel interface and the second one is called serial wire output port, which is SWO. Alternatively, trace can be also read out from ETF. And the next slide is S32K3xx Coresight infrastructure. Here I put a table to show you what sort of Coresight infra is present on which microcontroller. So few important things to look out here in terms of trace. Then SWO trace output ports have been made available for all the devices, but you have to keep in mind that SWO is shared with JTAG pin. And other important thing is parallel trace output ports are available only on S32 K314 and K344 variant. As I said earlier, the chip can be accessed via JTAG or SWD interface. In this microcontroller, each Cortex M7 core supports 8 instruction comparators and a watch point unit having 4 watch points, that is your DWT watch points. Talking about the same DWT, then it provides 4 hardware comparators which is shared among debug and trace systems. One information which I would like to share here is these hardware comparators can be also used as start-stop triggers for ETM instruction trace. And how to use this, I will show you in the later part of this webinar, which is live demo session. In the next 2 slides, we are going to discuss the specific debug feature of S32K3xx microcontrollers. So now let's have a look. The first one is debug from first instruction. Actually, this chip supports debug from first instruction upon system power up, or upon destructive reset, or upon functional reset. Actually, this feature is automatically enabled once a valid boot header is programmed into your application. So the next question will be, what happens when our application does not have a valid boot header? How the chip starts? Basically, the application core remains disabled. In our debug initialization, we ramp up some clocks, then initialize the SRAM, store a minimal image in SRAM, and then the core gets enabled. Actually, the cores are executing a branch to itself out of SRAM, and with the same sequence, a download to RAM and debug from RAM is possible. During the live demo session, I will discuss what are the required winIDEA configuration for this use case, and I will also perform this use case to get a better understanding. Moving to the next feature, which is secure debug. Here, secure debug signifies locking the debugger access through JTAG interface until the HSE firmware authenticates the debugger based on application debug key or password. Usually, the host debug is either open or protected during the device lifecycle, so this feature would be helpful in those cases. There are two authentication methods supported by this microcontroller. First one is static. In this case, debugger provides a password in plain form. And the second one is dynamic. In this case, key or password is a cryptographic key which the debugger uses to calculate a cryptographic response to a random challenge. One information which I would like to throw here is we support this feature, and if you have any further questions about this secure debug feature, then feel free to contact us. And the next slide is multi-core synchronization. As I said earlier, bidirectional core control is possible in this. So assume a situation where you have a multi-core S32K3xx microcontroller which works in decoupled or independent mode. So in this case, you can synchronize the core. And how this synchronization is done, for that you need to understand few things. Actually, we have a ECT, which is called Embedded Cross Trigger Module. And this ECT module has two components, CTI and CTM. And actually, these CTI and CTM help us to perform this core synchronization. Basically, the CTI provides a cross-trigger interface between the cores and the other debug and trace modules, whereas CTMs helps to interconnect the channels of these CTIs. Now let's have a look at synchronized core state while debug. So if you set a breakpoint on a core, then automatically the other core goes in halt state. The second one is if you start resuming or run one core, then the other core also goes in run state. And the third point is if you are performing single step or a step over or run until on a core, then the other core will remain in halt state. So these information you must be aware of about the multi-core synchronization. So far I have spoke about S32K3xx architecture, followed by that debug, and then specific debug features. So now let's talk about trace. So in this picture we see different trace sources like DWT, ITM, ETM. So it's good to know these trace sources in context of S32K3xx microcontrollers. So on this microcontroller, ETM provides instruction and data trace. It captures M7 processor program flow or data, and then it creates trace messages. Followed by that, those trace messages are getting forwarded to TPIU. In addition to that, one information here that ETM has 8 comparators which can be used for data trace or trace trigger qualifiers. If I say trace trigger qualifiers, it means using those 8 comparators, you can control the program flow trace. Now talking about DWT, then it implements 4 hardware comparator which can either serve as trace on-off triggers or as data access breakpoints or so-called data watch points. The trace data of DWT is being forwarded to ITM, which forms the trace messages, and then followed by that, these trace messages are getting forwarded to TPIU. If I talk about ITM, then ITM can also generate trace messages by itself. The software can directly write to the ITM stimulus ports, and data written to these ports are output to trace tools. Now at the end, let's talk about TPIU. Then TPIU receives trace messages from these 3 trace sources and can output the trace data through these 2 types of trace ports. So we have here a parallel trace port with 1, 2, 4 or 16 data pins and one clock pin, which is so-called serial wire output, which is an asynchronous single pin port. If I talk about S32K3xx microcontroller, then alternatively here, traces can be read out from ETF. But the problem with ETF is it has a very small size, depends on the microcontroller variant. It has 1 KB or 2 KB in size. So this size impacts the trace capabilities. So we have reached the segment of the webinar where the live demo starts. As you see here, I have divided live demo into 3 parts. First one, I will discuss about debug and parallel trace. I will tell you the tool setup, and then I will discuss these 3 use cases. Second part, the use case I am gonna show you is function profiling using code instrumentation, where I'll be using DWT and SWO trace capture method. Third part, the use case which I'm going to discuss is data trace of local variables, and I'm using ITM trace source with SWO trace capture methods. So our first part is debug and parallel trace. The tool setup which I'm going to use is, this is my host PC. I'm using Bluebox IC 5700. The Coresight 20-pin adapter is being used, and I have evaluation board with S32K3xx, which is a dual-core microcontroller, but the operating mode which I'm using is lockstep for my working project. So this is how my winIDEA looks like. I have already opened my project. If you want to open yours, then you need to go here, File, and then Workspace. By clicking on New Workspace, a new workspace will be created. And if you want to open the existing one, then click on Open Workspace, and then you can open it. Let's have a look at few other details. I'm using winIDEA 9.21.1. I would also recommend you to enable go to help support log and enable Eve, so that you can see what is happening in the progress tab. Apart from that, there are a few other important things which you must check before starting debug and trace. So let's have a look. Go to hardware, select your blue box. You can check the communication from here. It's okay. Then go to hardware and emulation option. You must select the controller which you are using. You can go to startup, and only you need to select this checkbox. If you go to applications, then you need to select your file, output file, press OK, and then OK. Now let's look further. Go to hardware and then CPU options. If you look at reset tab, then you must check this box, latch target reset. You must check this box, reset CPU after download. This checkbox is required when you go for debug from first instruction. Now let's have a look at SOC tab. There are many options available, so I will go one by one. Debug protocol, you can select here either JTAG or SWD. Now the second tab is use cross trigger channels. These two options are used to run the multi-core in synchronization. So if you want to enable this multi-core synchronization feature, then you must check these two boxes. I'm using S32K3xx, which is a dual core, but I'm running in lockstep, so this is not required. Now let's have a look at trace capture methods. So there are three trace capture methods available: parallel, SWO, and ETF. I will describe one by one and the settings required for it. Suppose you are selecting here parallel. Then you can select either JTAG or SWD. If you select here SWO, then you must select here SWD, as I have already told SWO shares pin with JTAG. If you select here ETF, then you can select here either JTAG or SWD. Now let's talk about when I select here parallel. So protocol will be either JTAG or SWD, so I am choosing SWD. Then you need to tell what is the width. So there are five options available: 1 bit, 2 bit, 4 bit, 8 bit, and 16 bit. These are the options available, and you must check what your device supports. If you select here SWO, then you must define this clock and pre-scale. One thing is pretty important here is clock divided by pre-scaler plus 1 should be less than or equal to 10 megahertz. So assume if your clock, the core running frequency is 50 megahertz, then you must define a pre-scaler of 4. Now talking about ETF. If you select here ETF, then there are two options available. First module is full and all modules are full. Actually, we have several ETFs for various sources. That's why these two options are available. And based on your selections, once these ETF buffer is full, winIDEA will stop the recording. Now let's have a look at TS generation. Basically, this is timestamp generation. So when you go for SOC global timestamp or ITM on-chip timestamp, then you can enable this module, or you must enable this module. So these are the basically options available in hardware SoC tab, and whatever I have explained, you must aware about this. Now let's have a look at cores CM70. So you must check this option, core reset. So it will catch whenever there is a reset, and this option is particularly required when you go for debug from first instruction. So you must enable this. Now let's have a look at winIDEA analyzer window, and this is how the analyzer window looks like. And how do you open it? So you go to view and click on analyzer window, and then this window will appear. The reason behind opening this analyzer window is to show you the ETM, ITM and DWT configuration in context of S32K3 and what are the options available. And if you want to go for instruction trace or data trace, how do you configure these modules? So here you see I have 2 ETM, 2 DWT and 2 ITM. The reason behind that is I'm using S32K3xx, which is a dual core. So that's why I have all the modules twice. Now let's talk first about ETM. If you want to use this ETM, then this module has to be enabled first. So let's enable this module. Now this ETM can be used for instruction trace and data trace. Apart from that, here we see 8 comparators. Actually, these 8 comparators can be configured as 8 single address comparators, or to perform the trace of 8 data variables. In the second way, we can use this as a 4 address range comparators. Why 4 address range comparators? Because when we go for range comparators, we need 2 comparators. That's why it shrinks down to 4. This address comparator can be also used to control the instruction trace. I will tell you what does it mean. If I say control the instruction trace, it means when we perform instruction trace, it traces all the active and inactive functions. But assume a situation where I am interested in only one function. In this case, I can use this address comparator to trace only a single function, not all of them. Now suppose you want to perform instruction trace. So in order to perform instruction trace, you need to configure this module. So you go here and then make it as true, press OK and select this option. So this module can be configured in this way to perform instruction trace. Now suppose you want to control the instruction trace and you want to trace only a single function. In this case, you need to use this address comparator. Right now, I will use this address comparator as a single address comparator. So I need to tell the comparator which function has to be traced. So now click on 0, go here, go for function, and suppose this is the function I'm interested in. Press OK. Here select instruction, press OK, and then again select the second comparator, go for functions, and look for the exit of this function. And select instruction here, press OK. And now you come back to instruction trace and tell start trace when comparator 0 condition is met and stop the trace when comparator 1 condition is met. So you need to select here 0 and 1 and you need to deselect this option and you press OK. So this is how you configure these comparators to control the instruction trace. Suppose right now this is used as single address comparator and you want to go for the range. Then in this case you need to just remove this and you press here 0 and you go for the range and say entire object, or maybe you can say range end on exit, select OK and press OK, and then you need to come back on instruction trace and then you use address range comparator and just you need to select here 0 and press OK. So in this way you can use to control the instruction trace but as a address range comparator. Now suppose you want to perform the data trace. So let me clear this off first. So in order to perform the data trace, you need to configure this module as well and enable ATV trigger. Then you need to come here, instruction trace, change this to store and press OK. And then you need to tell the comparator which variable you want to trace. So right now I will use this comparator as a single address comparator. So in this case you can compare 8 variables. So let me configure the first comparator and tell okay, task scheduler I want to trace. So please select task scheduling and then change it to write and press OK. And then you need to go here, data trace, and then enable this. Then you need to select this one and select 0 and press OK. So this is how you configure ETM for data trace. And suppose you want to go for a range, then you select here 0, click on this and then go for range, and then you can say okay, I want to trace the entire object. Then you press here OK, and then again you need to change this to address range comparator and press OK. So this is how you configure ETM in order to perform instruction trace or data trace. Now let's have a look at DWT. So if you are working with DWT, then first of all you need to enable this, and along with that you must enable this ITM as well. Here you have 4 hardware comparators which can either serve as trace on-off triggers or data access breakpoints. So if you want to use this for data trace, then you need to configure these comparators. So you can configure 4 data variable at a time in DWT. So let me show you how do you configure for a data trace. So you need to select this and then you give a write access and then select your variable like, and then you change it for this to sample data value. And now you suppose you want to use this DWT hardware comparator as a trace on-off trigger. I mean, you want to control the instruction trace. In that case, what you do, you select here which function you want to trace actually. So you change it to instruction execution. And then suppose, as I explained earlier in the ETM as well, so suppose you want to just trace this function in interrupt routine, then you need to select here and then you select comparator 1 as well. And then you select here the exit one. And now you go back to ETM and then you select, go for this instruction trace. And then you select, just you deselect this first here and select P comparator inputs. So start on 0 and stop on 1. And apart from that, I mean, these configurations are not required. Only you need to change these comparator inputs. So in this way, using a DWT hardware comparators as well, you can control the instruction trace. One thing which I would like to mention here is that you can trace 4 data variables here and 8 data variables here at a time. So in total, you can trace 12 global data variables at a time using DWT and ETM. Now let's move to ITM. Then if you look at ITM, then first of all you must enable this, and then there are 2 timestamps options. So suppose if you are using ITM on chip, then definitely you have to select this option, and if you are using SOC global timestamp, then you must select this option. And apart from that, here you see 32 ITM stimulus ports. So either you can select go for all, or either you can go for the selected ones as well. Like suppose if I'm just writing stimulus port 0 and 3, then you need to select 0, 1, 2, 3. Or suppose if you're using 0 and 1, then you need to go for 0 and 1. So either you can go for all, or either you can go for the selected ones, like the one which you are using. So now I believe you have a basic understanding of S32K3xx microcontrollers, their features, and the required winIDEA configuration. So now let's do or perform, I will perform all the use cases one by one now. So now let's go for our first use case, that is debug from first instruction. So already my application has a valid boot header. So there are few things which you must take is hardware, and then go to CPU options. This option must be checked, and you must select this core reset, because the expectation is when I first press this reset button, then my program should stop at the first instruction, and in the winIDEA window you can see a stop vector catch. So let's do a reset. So now you see program has stopped at the first instruction in the disassembly window, and in winIDEA stop vector catch option has been displayed, and now you can do the debug like this. Now let's move to our second use case, that is instruction trace. So few things you need to check first. Go to hardware, then CPU options, go to SoC. Here you can select either JTAG or SWD. I'm going for SWD. Trace capture method will be parallel, and then I'm going for 4-bit operation, 4-bit width, and then you press OK. And now you need to create a analyzer configuration for the instruction trace. I have already created, or you can create a new one by clicking on create new analyzer configuration. You can go for by selecting automatic, or you can go for the wizard option if you're not clear about the configuration required. I'm not going to in much detail, so I will go for the existing one which I have already created. So let me show you the configuration. I have selected here profiler, and then I have just selected here code. The other way could be you go here, go for the manual configuration, and then you configure this ETM for the instruction trace. This way also you can do it, but it's easier way. Just go for this profiler and select code, and winIDEA will automatically do everything for you. So you press OK, and now let's run the software first. My software is running, and now let's run the analyzer. So you see here, you can see all the active and inactive functions. So if you select this one, then you can see only active functions. If you deselect this, then you can see all the inactive functions as well. This is the profiler statistics view. I mean, you can see here which function has been called how long, how many times, and what is the net run time. Apart from that, there are these many options as well, like gross time, gross mean time, max time, average time, many things which you can select depends on your requirement. And this is the trace window where you can see the trace messages as well. One thing which I would like to mention here is that program flow trace can be also used for coverage analysis. So what you have to do is you need to click on this configuration, and then you select here coverage, and then press OK. And now let's run it again. So let's stop this. So now let's have a look at coverage stat window. So let's click on this. Actually, in this window you can find it out which line of your code has been executed, which line has not been executed. If it is in green, then it has been executed. If it is in red, then it's not executed, like these lines has been executed. Apart from that, you can also see if I talk about assume this test.c, then 94% of this file has been executed, 6% has not been executed. So I mean, these coverage analysis stuffs, you can find it out in this window, and this can be done when you have a program flow trace. Now let's go for our third use case, where I'm using I'm going to trace a global data variable using ETM. So for that, I have already created a configuration. So let's quickly have a look. I'm going to use blue box timer. You can use SOC global or ITM on chip as well. I will tell you when to use these different timestamps. So as a thumb rule, you use ITM on chip only if nothing else is available or to get the better accuracy, but this is in the expense of bandwidth. If I talk about global SOC, then it should be used for the on-chip trace buffer. So here in case of S32K3xx microcontrollers, when you use a trace capture method as ETF, then you can use this timestamp. And talking about this blue box trace timer, then this can be used for parallel trace ports or SWO, but you should never use this for OCTs, I mean on-chip trace buffers. Apart from that, you need to go to profiler and add the data variables which you want to trace. If you want to add a new one, then you go to new and click on trace, and then from here you can select your data variable. And interpretation, if it is a regular variable, then you set interpretation as regular variable. So let me show you for this one. This is a task scheduler. So I have selected this variable and interpretation as a regular variable. You can select here the observed code also. You can go for CM70 or the code in which this variable has been defined. Press OK. And now you go for this recorder and go for the manual configuration. Here you need to configure these two comparators for the two variables which you want to trace. I have configured this for these two variables. Now you go for data trace, come here, and then you select these two comparators, enable this, press OK. And apart from that, these two configuration you need to do as well when you are performing data trace with ETM. Now you press OK and press OK, and now let's run it. So this is how you can perform the data trace using ETM. Now let's have a look at SWO Trace. So as we know, all the S32K3xx microcontroller have this SWO Trace feature, but the problem is it has very less bandwidth. So use cases such as program flow trace won't be possible because less bandwidth confines our trace scope. Apart from that, there are a few questions like whether these two use cases like OS task, ISR tracing and profiling or runnable profiling is feasible or not. So the answer is yes, still you can do. If you are interested in OS task and ISR tracing and profiling, then it is possible by tracing the variable which is responsible for task and ISR using either using DWT data hardware comparators or you can use ETM comparators as well. And if you are interested in runnable profiling, then it is possible by code instrumentation using either DWT hardware comparators or ETM comparators. Here concept is the marking the entry and exit, where entry is always marked with a unique data and exit is always 0. But if you want to know more about these two use cases, then there are many webinars available on our iSystem YouTube channel, so you can see that, or you can visit our website for different application notes or knowledge base. So the setup which I'm going to use is rest of the setup remains the same, only the thing changes is I'm going to use Coresight 10 pin adapter, and using this setup I will be performing a use case function profiling using code instrumentation. And the next slide is here. This is the setup similar to the previous slide, and the use case I will be discussing is I will be tracing a local data trace variable using ITM stimulus ports. The use case which I'm going to present right now is function profiling using code instrumentation and using this DWT data trace. First, I will show you the part of the code and later the profile XML file. So let's have a look at the code. So this is runnable A, and I'm marking the entry and exit. So at the entry, I'm writing this data variable to 1, and at the exit it is 0. Similarly, for runnable B, at the entry it is 2 and at the exit it is 0. And similarly, I have marked the entry exit for the rest of the runnables as well. Now, this is our iSystem profile XML file where I have written 1 means runnable A and so on, and I have defined my data variable which will be used to trace. So now let's have a look at winIDEA configuration first. So hardware CPU options, and then I go to SOC. Then as my trace capture method is SWO, then protocol has to be SWD, and I have defined my clock and pre-scale. And then I did set up my OS. So I need to go to application. So this is an AutoSAR based OS which I'm going to use, and I have selected here iSystem XML. There are options like OT and RT files, and this is the XML file which tells our profiler, which variable has to be traced. If you want to know more about this, then do visit our websites or application notes or knowledge base, or you can feel free to contact us. I have already created an analyzer configuration for this, so let's have a look at it. You need to select operating mode as entry exit. This is coming from the profile XML file, and you need to configure the data variable in the DWT hardware comparator. So you need to go here, manual trigger, click on configure, and then I have configured this my trace variable function entry exit, and then you need to enable this as well. So click OK and then press OK, and now run the software and let's run it. So here you can see all the runnables on profiler timeline. If you enhance it, then you can see the function call as well, like runnable A, and it is calling A1, A2, A3. And if you look at runnable B, then B1 is being called, and then B3 is being called within B2. So this is how you do function profiling using code instrumentation. Here I have used DWT hardware comparators, but you can use ETM comparators as well if your chip supports ETM. Now I'm going to show you the another use case where I'm tracing the local data variable where using the ITM stimulus ports. So let me show you the part of the code where I have defined macros for different ITM channels, and part of the code where I am writing local data variable to it. So this is the two macros, and this macros is for the channel ITM channel 01. And the part of the code is here. If you look at here, then this is the local data variable I have created, and I am writing this local data variable to this macro ITM trace data. Let's have a look at the configuration. So hardware CPU options. This configuration remains the same, and I have already created an analyzer configuration for this, and let's have a look at that. I have enabled this ITM module, and I'm using just stimulus port 1, so I have selected here stimulus port 1. And apart from that, in the data area, I have added, you need to select here ITM and then channel as 1. You can give here a description like I have given channel 01 data. So press OK and then press OK, and now let's run the software, and let's run the analyzer. So in this way, you can perform the data trace using ITM stimulus port and obviously using SWO trace capture method. So this is the point where live demo session ends. But before I leave, I would like to show you Cortex M plugins which are available in winIDEA and can be useful. So let's have a look. View, you need to go to View, and then Cortex, you need to select here Cortex status. So here you see this cycle counter. So basically it is a DWT cycle counter which is a free running, and this can be used to find out the runtime between two breakpoints or using this you can find out the runtime of a specific function as well. Apart from that, you need to go to view and then select this Cortex fault reports, and suppose if you have any problem with your software like fault and exception debug, then you can come to this window and then you can see what sort of fault has been occurred, and using that you can find it out. So at this point I end this webinar, the technical part of this webinar from my side, and thanks attending for this webinar and listening, and feel free to contact us if you have any questions.
So thanks, Manish, for your presentation. And as we said before, now it's time for some questions. To all attendees, feel free to download the presentation now by clicking top right, the cloud symbol. But now it's really time for your questions. And Manish, I have a question for a first one. You used the 20-pin Coresight adapter for parallel trace, but the 10-pin adapter for SWO Trace. Why?
Okay, I mean, the basic difference between this, or I would say one of the difference between this 20-pin adapter and 10-pin adapter is the availability of the data trace lines, you know. And in order to perform the parallel trace, I must use I must have data trace lines, and then 20-pin connector provides that. So that's why I've used 20-pin connector for the parallel trace. And for SWO trace, I do not need data trace lines. I just need a clock, you know, SWO. So that's why, which is an asynchronous pin. So that's why I've used a 10-pin connector for SWO. And apart from that, one thing which I would like to mention here, as well, like, you know, when I go for SWO trace, I always select interface as SWD. The reason behind that is SWO and SWD, you know, both the things are always mixed with JTAG. And when I go for SWO, then I need a debug interface which uses less pins. So that's why I'm using SWO in combination with SWD, which is your serial wide debug.
Yeah. Okay. Thanks for the clarification.
I mean, like overall, with a 20-pin adapter, you know, you can perform both parallel and SWO, but with 10-pin adapter, you can only perform SWO.
Okay.
Yeah. Okay.
Thanks for the clarification, Manish. We have another question, Manish. Is there a way to trace data written by DMA, not by the core?
Actually, if I say, then I have not tried this, but I have tried in some other microcontroller, and I guess it is possible. So maybe I'll contact with my another colleague, and then I can put in more details, you know. But I guess it is possible.
Yeah, let's follow up offline again.
Yeah.
On that. And another question would be, you said that alternatively trace messages can be read out from the ETF buffer too. How is this possible?
Yes, I mean, you can read the ETF buffer trace messages too, and it is possible via using the JTAG or SWD debug interface. So using these two interfaces, you can read the ETF trace buffer messages.
Okay.
Yeah.
Thanks. So, okay, I think that's it. Obviously, you were very clear and detailed. No questions are left. So if questions come to your mind later, of course, feel free to reach out to us to webinar@isystem.com or to your direct tech or sales representative at iSystem. And before you leave, I would like to give you some additional information. Please leave us your feedback in the poll on the right side of your screen. Would be very much appreciated. If you have suggestions for new topic, please enter it in the questions tab. And feel free to check out our online trace tutorial, our webinars on our YouTube channel. This will be hosted there too in some days. And if you want to, feel free to register to our newsletter, where you receive updates for webinars, for example, or about new products automatically. So thanks, Manish.
Yeah.
For your time, for your presentations. And let me just repeat it. If you have questions, feel free to reach out to webinar@isystem.com or your tech or sales representative. So thanks again. Thanks for your time. Thanks for your time, attendees, and bye and take care. See you for the next webinar. Bye.
Bye-bye.
Bye-bye.